So far, we have written electron configurations for neutral atoms, where the number of electrons equals the number of protons. We can also write electron configurations for ions. We start by writing the electron configuration for the neutral atom. For anions, which have extra electrons, we add electrons using our normal filling rules. Follow the same order as usual for subshell energies and add electrons into no more than their maximum capacity. For example, the neutral chlorine atom has an electron configuration ending in 3p5. The chloride ion has a -1 charge, which means it has one extra electron. So we need to add in one more electron into our configuration. Since the 3p subshell can hold one more electron, we put it in there to make 3p6. Remember, for anions, we add electrons. For cations, which have a positive charge because they have lost negatively charged electrons, we need to take electrons out of our electron configurations. This is where it gets tricky. We aren't necessarily taking it off the last subshell we wrote in. Instead, we are taking it out of whichever subshell has the highest value of n. For the sodium ion, the 3s subshell has the highest value of n, 3. Because the sodium ion has a +1 charge, we take away one electron, and it comes out of that 3s subshell. We are left with 1s2, 2s2, 2p6. Taking electrons away from the highest n is going to be especially important for transition metals. Remember, the Ds have a lower value than the S's of each row, so we will end up taking out of the S subshell before taking out of the D subshell. For iron 2+, we take 2 electrons away from the 4s because that subshell has the highest value of n. We end up with argon core 3d6 as our condensed electron configuration. To make iron 3+, we take 3 electrons away. The first 2 come out of the 4s, which has the highest n, and then the last one has to come out of the 3d. Which is the correct ground state electron configuration of the phosphorus 3- ion? Is it A, 1s2, 2s2, 2p6, 3s2, B, 1s2, 2s2, 2p6, 3s2, 3p1, C, 1s2, 2s2, 2p6, 3s2, 3p6, or D, 1s2, 2s2, 2p6, 3s2, 3p3? The correct answer is C, 1s2, 2s2, 2p6, 3s2, 3p6. We start with a neutral phosphorus atom, which ends in 3p3, and then add 3 electrons because it is an anion. Which is the correct ground state electron configuration of the calcium 2+ ion? Is it A, 1s2, 2s2, 2p6, 3s2, 3p6, B, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, C, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, or D, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1? The correct answer is A, 1s2, 2s2, 2p6, 3s2, 3p6. We start with a neutral calcium atom, which ends in 4s2, and then take away 2 electrons from the subshell with the highest n because it is a cation. Notice we end up with the exact same electron configuration as we got for the previous problem with the phosphide ion. We would say that the calcium ion and the phosphide ion are isoelectronic. Atoms or ions with the same exact electron configuration are isoelectronic. They end up having the same number of electrons as each other. This is fairly common because atoms will often gain or lose electrons as they become ions, such that they end up with the same electron configuration as the nearest noble gas. For example, the phosphide, sulfide, chloride, potassium, calcium, and scandium ions all have the same electron configuration as the neutral noble gas argon. They do have to have the same exact electron configuration, not just the same generalized or valence electron configuration. For example, krypton and argon are not isoelectronic, even though they both end in ns2 and p6, because their n values are not the same.